Okay, so according to a couple people, somehow it's accepting one answer or one way of writing in the answer as correct and one way of writing it as incorrect for that last problem. I will look at it more carefully. And as you heard me say, I was working with David and the crew, and I'll have to use this instead of the bowling ball because I can't find my little S yet.
Can we go over like one of the questions in the homework?
Yeah, sure. Before I get started, let's just go ahead and do that. What's your question, sir?
So number three, part C.
All right.
I know the answer. I just don't know the answer.
Okay, so we've been working on this with students in my office, and so you have it available to you on OneNote. So everybody's using OneNote except for you, right?
Yeah. I don't have OneNote. It's fine.
But you can get it.
I know. I need to just sign up. I know.
Okay, so problem 3 is the problem that is having you find the acceleration of gravity due to 2 different objects and then the total acceleration of gravity for them combined. And so the first thing, and I found this a nuisance because their wording didn't make me think they were going to be paying attention to this, but they are. What direction is the force of gravity at this point? If I put some little mass here, doesn't matter what the mass is, if I put some mass where my orange dot is, what direction is the force on that dot going to be due to M1? Of course, you're pointing the opposite direction that it is on my screen. I was like, what? Yes, that is correct. It's always attractive. So you would have force of gravity 1 is pointing to the left. And what about the force of gravity 2, the force on that same point due to M2? This time I didn't even look. I just said, oh, she's wrong, so she must be correct. Well, because of the opposite. Yeah, because I'm harsh that way, you know. Okay, so Oksana and Judith just get them. So we have the directions of the forces. Now the problem defines that this is the positive direction. So that means that if we're dealing with mass 1, we're going to have negative for our direction. If we're dealing with mass 2, we're going to have positive for our direction. That's the thing that I would have myself put in wrong the first time through, because when I read the problem, I'm just saying, it doesn't say the vector, it just says find G without a vector sign, and so that's a positive value, just like, G is 9.8 meters per second squared, its direction is down. Question, ma'am.
So can we have points back for that one too?
Can you? Okay, I will go through and do that. But only for part A, because if you went on to part B and put in the wrong sign, that would be.
Okay, so you're gonna give us points back for A and for the other one where it's like the units were dumb. Yeah, the parentheses.
I have to look at that one. I can't give anything affirmative on that because I haven't looked at it yet. It could be that your answer was wrong and you don't realize it was wrong, or it could be that it was right and they didn't realize it was right.
It was right.
It was right. It was right. The end. Okay. Now, the definition of G is the force of gravity divided by the mass of one of the objects. That's why we don't have something where my orange dot is. If we put some mass of 5 kilograms there, then the force due to M1 would be G1 times that 5 kilograms. And so I wrote the full equation. I put it in vector form there, just putting the R hat A1, where A1 is the direction going from A to mass 1. So that has the directionality that allows me to throw the minus sign here because it's to the left. So the full equation for the force of gravity is G, mass 1, mass 2 over R squared. R is the distance between the center of mass of one object and my second object center mass. So for mass 1, it's going to be, that's an L. You can tell it's an L from the writing, but in the picture it looks like an I. So the R is going to be LA, and G, M1, and then the mass that's not even here is what cancel out. And so we just have minus because of direction, GM1 over LA squared. And then part B is just putting in numbers.
C is what the problem was.
And so C, what's the difference in A and C?
Is it like you just have to do L2 minus LA?
Right, this distance here is L2 minus LA. And so for B, you're going to have, it's now M2 instead of M1 because you're looking at a different mass. And then the second mass here is, again, the M I put without a subscript because it's the test mass, and that's what we divide out. And so now we have M2 on top instead of M1, and we have the difference in position L2 minus LA. And of course, quantum squared because it's R squared. And then just to finish out, part D, you put the numbers in. Part E, it says, what's G1 plus G2? Yeah, you just add them up. So literally your answer for part F is going to be your answer for part A plus your answer for part C.
So the expression,
Or no, I guess that's E. For E, it's going to be, Yeah,
the expression is literally
the expression is just the expression you put for A plus the expression you put for C. Yeah, it's
Hold on. And I'm terrible.
it's kind of trivial once you get to that point.
I told you.
You good, Randy?
Yeah, that answers my question.
All right.
It's all parentheses.
It's all parentheses, which apparently is what I'm going to be checking after class. Okay. Last class period, we talked about the gravitational force. We just did a universal gravitation example. I will remind you, units are important. Problem 4. Problem 4, you use the equation that I worked out in class for using Newton's second law combined with centripetal acceleration to get t squared is equal to 4 pi squared over gm times r cubed. Now, 2 students in my office both had written down without the square on the pi, which suggests maybe when I squared 2 pi, I didn't put the square on the pi. And so you're just using this equation for problem 4, but units. I converted everything into the standard units, so I converted from solar masses to kilograms, from light years to meters, and then I got my time in units of, what's the standard unit for time? Seconds, and then I had to go from seconds to years. You can do things other ways, but that is the way that I think is the best practice for unit conversion and keeping you sane. Some people's calculators were not up to the task. If all else fails, Excel did not have a problem with the math. I didn't try Google Sheets, so I can't guarantee. Because the numbers are large, there can be issues. So that's what we looked at. Today we're going to be looking at work. So when I say work, what does that mean to you? Okay, units are joules. The unit for work turns out to be a joule, and we'll define what that is in a little bit. What else does work mean to you?
Money.
Money. She thinks of money when she thinks of work, right? Because most of the time we think of work as toiling for money, exchanging our skills for money. But in physics, work is something different. And specifically, we will be focusing exclusively on mechanical work. Mechanical work is a force acting on something and making it move. So a force acting on something with no motion, not work. So if I go to the gym and somebody puts, 400 pounds on the bar and I'm like, oh, I can totally bench press this. I get under there and I can push as hard as I want. But that bar doesn't move. Yeah, that is embarrassing, but that is absolutely what would happen. I didn't do any work according to physics. There was no mechanical work done because there was no motion associated. I certainly put a force on it, not 500 pounds, but put a force on it, but there was no motion, hence no work. So work is force with motion, and in fact, that motion has to be parallel to it. Now, I have this sitting here, and I can't help but play with it. It's supposed to have the bowling ball, but like I said, I couldn't find my little S thing. I tried making up using some other stuff once. It swung, it broke, it was not good. I had to drill a second hole and put my, yeah. So if I swing this, why does it swing back and come back, or over there and come back to me? Okay, she said momentum. Inertia. Gravity. Okay, we have some different answers, but it looks like we're not really clear exactly how it works. If we use what we have learned so far, when I am holding this, of course, everything we've learned so far had to do with forces. So I'm applying force to hold this up. This is applying force that way, a tension force. Not strong enough to make it straighten out. There's gravity pushing down on this. When I let go, what does gravity do?
Pulls it down.
It pulls it down. But because of this, it can't fall straight down. It makes it change direction. But it's moving because gravity was applying a force. And Newton's second law says force, the net force, will cause an acceleration. And so we can explain it that way. But then, when it was at the bottom, why did it keep going? And somebody had a word for that. With two people. What? Okay, inertia or momentum, which we haven't talked about momentum at all yet. So I'm going to go with inertia. They work together hand in glove. So it was moving, and something's going to have to apply a force to make it stop. So it kept going, but as it was coming up, gravity had a component that was pushing down, that stopped it, right? Now, we're going to learn today to describe this using a different way that is simpler. Now, you might say, wait a minute, we spent all this time with Newton's second law, and you're now telling us there's a simpler way? The answer is yes. But the reason we do that first is because you have to understand the forces and how they work before you can do the simpler way, before it makes sense. So let's get into that. I'm going to skip this, talking about energy. This is a good old slide just to get you thinking responsibly about energy. You have sources of energy. Okay, I said I wasn't going to. I'm going to stop here and what do you see in here that has some kind of energy associated with it?
The sun.
Okay, the sun. Plants. The what?
The wind.
That you can't see.
Yes, but they have the windmill, so you think of the wind.
Right.
Okay, somebody said light. I'm just going to.
Of course, there's the windmills.
Yeah, well, I got the wind. Okay, now let's break it down some. Because this is where things get a little interesting. The wind. There is energy associated with wind. What causes the wind? Did you say? No. Okay. What I thought.
Weather patterns.
Okay, weather patterns. We have, when it's hot, gases expand. When it's cold, they contract. And so you get places with higher air pressure, lower air pressure, and those pressure differences. Remember, pressure is a force, or we didn't talk about pressure, we just talked about stress, right? We haven't gotten to that yet. But pressure is a force over area, and so you have a net force that's pushing harder in a high pressure region, not as hard in the lower pressure region, that makes it move. And so winds are caused by temperature differences. And what causes temperature differences? Fundamentally, it's the sun. And so all the wind energy derives from the sun. Plants. What kind of energy do we have in plants? Sorry, what was that, right?
Photosynthesis.
Okay. Plants convert energy through the process of photosynthesis. But what they have is chemical energy. The photosynthesis is a method of converting from one form to another. They have chemical energy, and we consume that chemical energy, and our bodies also can convert that chemical energy from one form into another that allows us to do stuff. And then waste, whatever. I'll stop at that point before I get to anything crude. So, where does the chemical energy come from in the plants? And that is actually, the photosynthesis process is part of them storing the energy, isn't it? I'm not a biologist, so. But neither is Randy, yeah. And so, ultimately, actually, the energy that's stored in the plants is coming from the sun.
We're all talking.
You have, no, we're not. You have atoms in the plants that are converted through solar energy into a higher energy state and store the energy, and then they can convert it to a lower energy state and return it. So the sun is our source of plant energy, wind energy, obviously the source of the sunlight energy. Why is the sun giving off energy to begin with?
Because energy is just thermal heat or something. In a way, I guess you could say.
Thermal, that's a form of energy.
Well,
But why is the sun releasing it? Why isn't it holding it in?
Is it like a big reaction?
Yeah, I keep waiting for, because David was talking about the song this morning, the sun was a giant atom smashing machine.
yeah.
Hydrogen is built into helium at a temperature of millions of degrees. Yo ho, it's hot, right? Okay, so it's nuclear reactions that are causing the sun to release that energy. That sun energy makes over 99% of the Earth's energy budget. Without the sun, we need its light, we need its heat, we need its energy. Just going back to that song David was making fun of.
Yes.
Without the sun, without a doubt, there'd be no you and me. Rainy?
I see the Vsauce, it's kind of, I see the Vsauce video where they were talking about how there's like creatures below the sea that use thermal energy from like the Earth's core to survive, basically. So they don't.
Where's that come from? That's the other less than 1% of the Earth's energy budget. Where's that come from?
The Earth's
Yeah, but why?
You'd have to go from the formation of the.
One of the two things is heat left over from the formation of the Earth, because mass fell in. It's magic. Mass fell in, made things hot, and that energy is still coming out. But then there's a second thing. There are nuclear reactions occurring in the Earth that are the rest of that. So all of our energy comes from either nuclear energy or from the formation of the Earth, the compression that occurred. See why I wasn't going to talk about this. This is a lot amount of time, but when we finish energy, I'll talk about energy conservation and our responsibilities, and then we'll spend more time talking about things that aren't specifically physics, but are about why physics is important in life and our responsibilities. So here's the definition of work. The first line equation, you have a question, Russell?
But isn't the sun's reaction all about physics?
Is it what?
Isn't the sun's reaction all about physics?
Yes. Yes. And we will cover that next semester. The definition of work is work requires a force and motion parallel to the force. And I have the first line is first a calculus equation. If you understand calculus, that's exactly the definition of work. Integral of force dot dx. What does a dot product mean?
Let's respect to direction, right?
A dot product means you're multiplying only the parallel parts of two vectors. We've been doing a lot of work with vectors. Here we have a calculation where we're multiplying the parallel parts. Now, because this is not a calculus-based class, I have the second thing on that first line, F dot delta x, the force times the change in motion in the same direction. It's as close as we can get without calculus to the first one. The line down below is probably more useful to you because the dot product, how much is parallel? Well, if I have a force like this and motion like this, I want to multiply only the parallel parts What would I do with that delta x to find the parallel portion? I'd break it into components. So I would have like this and like this. If theta is the angle between force and delta x, what is the component of delta x that's parallel to the force? It's the adjacent side, so it's the cosine. So the adjacent side here is delta x cosine of theta. And so that's the parallel, the force, the distance traveled parallel to the force, and then times the force. So we have some examples here. Dude here is pushing the lawnmower, showing off his burliness, apparently. And he's pushing the lawnmower down the handle. What's the point of the downward force to the handle?
Keep the lawnmower around.
Yeah, because otherwise the lawnmower is always floating up in the air. It's such a problem. If you pushed it just forward, maybe, I don't know, maybe the front wheels catch on something and the back end kicks up and they steps into it. I don't know. But when I push a lawnmower, I have mostly forward force. I try not to push down too hard because that's just extra. Only the forward force is going to make it move. And so if you calculate the work he's doing, it's only the forward force times the distance he moves that's the work. The downward force isn't doing anything useful. And so it's not part of the calculation for the work. Now let's look at some other cases here. Gentleman with the briefcase. Or me with the bowling ball. So, standing here holding the briefcase. What's the work I'm doing on the bowling ball right now? None. Why? Not moving. Okay, so now the next picture, you can see barely. He's walking like this. What's the work he's doing on the bowling? Well, on the briefcase, me on the bowling ball. Walking at constant speed.
Forward.
I know it says the answer there. What's the work I'm doing on this thing?
Is it nothing?
It's nothing. Why is it nothing? It's moving this time, right?
If you were swinging your arms or something.
Well, I mean, it's moving at constant velocity. Why is there no work? My force was vertical, but the motion was horizontal. So the parallel motion was zero.
Wait, repeat that.
The motion was horizontal, but the force was vertical. So there's no parallel motion to the force. There's motion, but it's not parallel to the force. So there's no work done there as well. So apparently this gentleman has been lazy because he's, not doing work. What would he have to do work on his briefcase? Curl it. Right. So we curl this bad boy, or in his case, it doesn't show a picture. It just shows him going upstairs with he's disappeared. He turned into ghost form. So if he raises it, then there's motion parallel to the force he's applying and there's work he's doing. In the case of him walking up the stairs, his force is vertical. The motion has a vertical component. And so you take that vertical component multiplied by the force and that gives you the work. Graphs are useful if you don't have calculus. If you have calculus, these are just redundant. So if we make a graph with the force, now this has force cosine theta. In other words, this axis is the force parallel to the motion. So if you have the force parallel to motion on the vertical axis, and then you have the distance traveled on the horizontal axis, then if you take a segment of motion and you take the force and multiply, well, the force is this here, and multiply it by the distance traveled, then the area here is equal to the work. Now, that works great if you have a constant force. But if you have a constant force, you didn't really need that visualization. But if the force is varying, you have two options, calculus or graph. If the force is varying, what you can do is you can break the force up into a bunch of little tiny motions and get the average force for that little motion. And so that's what this is supposed to be illustrating. In this motion period, the average force was this height. And so it takes the average force times this width plus the average force for this one times this width and adds them all up. And once again, the area under that curve is the work done. Now, if you have something like a spring, does anybody remember the equation for the force of a spring? So force is kx. That's the magnitude of the force, the direction. We didn't put a sign on there because we don't care about the direction. So if I make a graph for the spring force in units of newtons and the stretch in units of meters, what should this equation, force is equal to kx, look like? What is this the equation of? That is, well, yes, it's the force of a spring is absolutely correct. But when I'm making a graph, what does the shape look like if I have y equals kx? Y equals mx plus b. What's that equation for? A straight line. And so this is going to have a straight line. And so if I have a spring that starts here and ends here at some x final, then the force here is, of course, kx final. And I have a triangle for the area under this. How do you find the area of a triangle?
1/2.
Yes. The area of the triangle is the area under the curve. Yes. So 1/2 base times height, which would be 1/2 my base, which is x final minus 0, times my height, which is kx final minus 0. So that's 1/2 kx final squared. So that's how much work had to be done to stretch that spring. And of course, this is just a function of x final, so if x final is bigger, it's more work. And so we can calculate the work required to stretch the spring by using this graphical method. Let's just jump straight into a problem. A package on a roller belt is pushed horizontally through a distance d, and notice that d is given to you. And I'm going to ask four questions. Work done by 5 questions. Force applied, force of friction, the force of gravity, and the force normal, and then the network. So work with the people at your table to come up with answers for this. And it should actually go pretty quickly, right? This is not a super complicated thing.
Alright, so look.
It's not falling. So if it's not work, I'm not working with you. And so look, force applied, force over distance, 120 times. Well, no, 120 minutes.
Is 120.
Because it's very,
Would force apply be like the 120?
The lower case have a spreadsheet.
yeah.
No, it's just one.
There's no theta. So it's cosine force times x times cosine.
Not half that, or half. We mentioned
Force
120 minus.
applied is just.
Well, it's volts.
The time to work.
Also, what's
That was
time?
where you used to
Yeah, that's my
It's like, hey, 120. Not minus five. Who's trying to work? Who's trying to work?
We'll put that there for you, David.
Sorry. Then we have to do
Which one is
the
friction? 2800.
Exactly. Exactly. That's that. So the force supply equals 120. You're trying to ask for. So then the force friction is going to be 5 times.
That would be resistance to actually.
That's a negative friction.
Wouldn't we just do like force
Then
supply
you go by.
equals 20 times?
So the whole system is really just.
Yeah, force supply. So don't we have to find all
Times
the forces
the-
first? And then
Yeah,
find-
what'd you get for 5 times? Try really. I'm also gonna go
Wow.
Does thing that changes this in this problem? Change.
The forces are fixed or directions.
Oh, this is the fixed direction.
Work done from friction is negative.
Take the negative.
What is
You know,
left your sign
That's what I mean.
But he wanted to force.
And that's the force of application.
Why
And then.
121 is 5. It's just a
5
system.
in the other direction.
No, but
Like you do we use the 5
Because it's going to be other way for the plan.
We will. I think people have done a fair amount of work. One group appears to be done, either that or they're just having too much fun. So let's look at this now that you've struggled with it some, so that we can clarify thought if there is any need for clarification. The work is force times distance parallel. So let's just do them one by one. Force applied is the first one I listed. What's the angle between force applied and distance?
None.
0. What's cosine of 0?
0.
1.
1.
Yes.
Okay, so that's going to be easy. I'm going to have 120 newtons times 0.8, that's 96, times 1. So I have 96. What are the units? Newtons times meters.
Oh, that's not wrong.
Newton meters. And a Newton meter, we abbreviate a joule. Now, joule is spelled as a person's last name, and it's not Elias. And of course, you're supposed to use a lowercase here when you talk about the unit of capital, when you use the person. So the unit there is joule. So we have 96 joules of work done by the force applied. Now, what about the force of friction? What's the angle between the force of friction and the distance?
It's negative.
180.
180 degrees. And what's cosine of 180 degrees?
Negative 1.
Minus 1. And so we're going to have 5 times 0.8, that's 4, times minus 1, so minus 4 joules.
Why isn't the force of friction negative if it's going the other direction?
Well, the magnitude is 5
Oh, okay, that's the magnitude and then
Yeah.
Gotcha.
because the cosine is taking into account the directions of both of them. That's a good question. What did you say? Okay, now on to the force of gravity, W. Okay, we got no neck slash gestures. Oh, I know. Totally cool. It's just in the NFL. If you do anything that is anything close to this, you're gonna get a NFL. And so going like that. Yeah, you don't see that anymore.
No,
Okay, so why are these gentlemen saying no?
because it's vertical and not horizontal.
Because the angle between them is 90 degrees. What's cosine of 90 degrees? 0. Okay, what about the normal force? Same thing. So our answers were 96 joules minus 4 joules. 0, don't need to put units when it's 0. And 0. And keep in mind, this is the work done by these forces. Those are not the values of the forces, or else you'd have something really weird. So I'm putting W here because you know what? When you look at these slides without listening, you'll be like, what? Force is equal to joules? I didn't think that was the right units. It's not. What's the network then?
92.
92, just add them up. All right, that wasn't tough, was it?
If you did like a regular force diagram with like the little box and all
Mhm.
the forces, then the friction and the normal forces cancel out anyways.
The force of gravity and the normal force in this problem do, yes. Andy.
Is there any reason why you wouldn't want to add up the forces going in the same direction first and then calculate the joules from the
It would be
network?
like
My key of not doing that was because I wanted to make sure we understood how you can have positive work or negative work.
Okay.
Right, because you could have done the net work just by taking the net force, multiplying by the distance parallel to the net force. Yes, Judith.
Wait, so how do we get -4 for our force of friction?
Okay, so if you look at the force of friction is to the left. And the distance is to the right. So the angle between those two is 180 degrees because they're opposite of each other, anti-parallel. And cosine of 180 degrees is -1. So when I put the magnitude of the force times the magnitude of the distance times cosine of the angle between them, that gave me 5 newtons times 0.8 meters times -1. So if the force is opposite to the direction, it's going to be negative work. Does that make sense? Okay, potential energy. I haven't even defined energy, have I? Well, energy is the ability to do work. If you have energy, you have the ability to do work. Potential energy is the ability to do work because of position or configuration. So for instance, this bowling ball, if I hold it here over my foot and I let go, what's going to happen? It's going to hurt my foot. It's going to apply a force to my foot. My foot is going to crush, so there's going to be a distance involved. Force times distance is work. It's going to do some work on my foot. Why would it do that work? Gravity. Because of the force of gravity and its position, it can do that work. If I started with it down here and I let go, there ain't no work. But it could do it up here because of its position. So we call that potential energy because it has the potential of doing work because of its position. Chemicals, in chemistry, you have chemical potential energy. It has the potential of doing work because you have bonds that are in a higher energy state than you could otherwise have. Randy.
I just had a question because it says something about storing energy. And I see it says that in potential energy A, the work done to lift weight is stored in the mass.
So the calculation of the potential energy is what Randy is going to. The calculation of potential energy, how much work can gravity do on this ball when I hold it out here? Well, I have the force of gravity is going to be the same mg as long as I'm here on the surface of the earth. And it can drop that distance of the height. And so the total work that gravity can do would be mg times h. And so that's what we call the potential energy. The potential energy is actually defined as minus, well, the change potential energy is negative the conservative work. So the conservative work, I'll get into conservative more on Wednesday, but conservative means that if you do work on it, it will give you back that energy. So with this bowling ball, if I lift it up, I had to do work on it, right? I had an upward force, it moved up. I was working against gravity. And if I let go, gravity is going to bring it back down, returning all of that energy that I put into it. So gravitational force is conservative because it will give back what I put into it. Yeah, Randy?
How fast is gravitational force?
There's not a speed associated with force.
So as soon as you drop it, it's like it falls down.
Yeah.
I don't know.
There's not a delay between when I let go and when it falls.
Just heard something about the speed of light.
Okay. That is a question of how quickly does a gravitational wave travel.
Yeah.
And theoretically, it travels at the speed of light. Theoretically, I say because I don't know what the latest research is. It's only the last couple of years that we have actually detected gravitational waves so they can start actually trying to make some measurements of their properties. So I'm kind of ignorant about what the latest is on that. But I know theoretically, the gravitational wave travels at the speed of light. Okay, so work conservative is defined, well, potential energy is defined as change of potential energy is minus the work conservative. And so for gravitational force, there's a potential energy because you can get your energy back for gravitational force, and its potential energy is mgh. So this picture here is actually illustrating how like a cuckoo clock or whatever. I don't know, my grandmother used to have a clock that had weights like this. And how it works is, my grandma would come and she'd pull this string down and the weight would go up, and that was it. I was like, that's crazy. How's this work? Well, how it works is when she pulled the string down, she pulled the weight up. She did work on that weight. She applied a force. Now, her force was down, and the string she was pulling on moved down, so she did a positive work. And that positive work was done on the hanging mass to make it rise against gravity. And so then that energy was stored, and the clock slowly allows the mass to drop and convert the energy from gravitational potential energy into the energy making the clock operate. And so instead of having a battery or a cell, and a battery is just a battery of cells, it used gravitational energy to run the clock, which is really kind of cool. Don't have to go buying gravitational energy packs, you just go. Kinetic energy, ability to do work because of motion. Remember, we studied kinematics, motion. And so we all know, if I had Randy stand up in the middle of the aisle, and I ran at him, when I hit him, I would apply force to him. And what would happen to him when I applied force to him? He would stand dead still. Yeah, that's the way it works. Shall we try?
Yeah. That's a challenge.
No, we will not. He would move as a result of me hitting him. And so I hit him, he moves parallel to that, I apply the force times the distance means I do work on it. Why was I able to do that work? Because I was moving. And so we call that kinetic energy. And at this point, I'm just giving you the equation for kinetic energy. Actually, if you look in the lab guide, I actually show the integral of how it's calculated and stuff. Kinetic energy is 1/2 mass times speed squared. Now, this is something that plays out in football all the time. You have this little defensive back. Who would you rather run into you at full speed? Me or
Max.
I'm looking for somebody who's noticeably lighter than me. Max may be lighter, but it's not light. I'm thinking David here. David knows I'm thinking him. So, would you rather have me or David run at full speed and hit you? I know your answer is I don't want either of you to do it. It depends on the full speed.
True.
It depends on the full speed. So let's suppose that we have the same full speed. Who would you rather have run into you, me or David? David, why? Less mass, hence he's got less kinetic energy, less ability to do work because of his motion. So in football, you've got this little defensive back, he's like 180 pounds, little flimsy dude. Yes. And so you've got a defensive lineman that's like 320, and those dudes can motor, okay? They don't run slow like me. You don't want to get hit by that defensive lineman at full speed. You'd much rather take the hit from the defensive back because of the difference in mass. But what if the defensive back is way faster? Now, of course, the difference in the top speed for a 350-pound football player and a 180-pound football player, percentage-wise, isn't that big. You're comparing my speed with any of them, it's really big. But if the defensive back could run like 50% faster and he weighed half the weight, had half the mass, Well, 50% faster, 1.5 squared, 2.25, divide that by half, and you have more kinetic energy. And so the little guy running twice the speed would be more damaging than the big guy at twice the mass but half the speed.
You could kind of apply this to like cars, right? You know how they're trying to save weight and stuff like that to get a faster speed, or if they go fast and they save weight.
Although we try not to crash cars as much as we do football players. That's the sole reason I'm talking about football players, since they crash into each other all the time, right?
Right.
And ideally, they don't break their necks and they do it right. Ideally. Now, there's some other things on here that are very important. So we have energy we can have in motion, kinetic energy. And then we have this thing we call the work-energy relation. Because remember, I said energy is the ability to do work. So there needs to be a relationship between them. They're going to have the same units. What are the units for energy then? Joules. And the net work done is equal to the change in kinetic energy. So in that problem that I gave you with the two forces, force of friction and the force applied, the net work, which came out to be, 92 joules, that would be telling me about the change in kinetic energy. So it's going to be speeding up, and I don't remember if we even gave you a mass, but you would just say, okay, the change in kinetic energy state starts at rest. The change in kinetic energy is the final, 1/2 m times v final squared, minus initial, 1/2 m times 0 squared, is equal to that 92 joules. And so based on the amount of work done, you can calculate how the speed's going to change. And that's where this gets us problem solutions easier than what we've been doing with forces. With forces, we had to do, well, more work. So I'm gonna work a problem. Oh, I'm not gonna work a problem here because I have 1 minute left. Since network is changing kinetic energy, and network can be broken up into the conservative work, the work that's the energy is going to come back to us, and non-conservative, things that aren't going to give you energy back, are things like friction. If I slide this, friction made it stop, and friction is not going to make it come back. Right? It just took the energy away, put it into something else that's not useful to us. Using the definition that the work conservative is minus change in potential energy, then you just substitute that in here, and the net work is minus change in potential energy plus work non-conservative. Solve that for work non-conservative and use net work as change in kinetic energy. And you have the non-conservative work is change in kinetic energy plus change in potential. And next class period, we'll be doing problems with this. For lab tomorrow, when and where are we meeting? 2:30 at Urban Air. Don't go to where Defy Gravity used to be. It's now Lincoln Madhouse, and they're not open on Monday or Tuesday. So don't go there. I sent you email. You should have directions to the Urban Air. It's just on the other side of Holmes Lake, close, 70th and close to Van Dorn. Before you go, make sure you fill out that waiver so you don't have to do it when you're there. We got 2 hours. You can do Ninja Warrior. You can do whatever you want there, except for I'm going to videotape each one of you jumping up and down for you to analyze.
I'm not.